For decades, classical computers have been the bedrock of our digital world, transforming every aspect of modern life. From smartphones to supercomputers, these machines process information with incredible speed, driving innovation and connectivity. Yet, as we push the boundaries of scientific inquiry and complex problem solving, we encounter a new frontier where classical limitations begin to emerge. This is where the enigmatic realm of quantum computing steps in, promising to unlock computational powers once thought to be purely theoretical, redefining what's possible in the digital age. At the heart of every classical computer lies the bit, the most fundamental unit of information. A bit is elegantly simple, capable of existing in one of two distinct states, either a 0 or a 1. Think of it as an electrical switch that is either off or on. These binary states are the language through which all data is stored, processed, and transmitted. From the complex algorithms driving artificial intelligence to the simple text messages we send, everything breaks down into long sequences of these zeros and ones, meticulously arranged and manipulated. Quantum computers, however, operate on an entirely different principle, one rooted in the peculiar laws of quantum mechanics. Instead of bits, they utilize qubits. While a classical bit must be either 0 or 1, a qubit harnesses the power of quantum phenomena to exist in more complex states. This isn't just an incremental improvement, it's a paradigm shift in how information is encoded and processed. Understanding the qubit is the first step into appreciating the profound capabilities of quantum computation and its potential to solve problems previously considered intractable. The most fundamental difference lies in a quantum phenomenon called superposition. Unlike a classical bit, which is definitively 0 or 1, a qubit can exist as 0, 1, or, astonishingly, both simultaneously. Imagine a coin spinning in the air. Until it lands, it's neither heads nor tails, but a combination of both possibilities. This both state allows a single qubit to hold far more information than a classical bit. It's akin to having many potential answers at once, dramatically increasing the computational density of the system before any measurement locks in a single outcome. This simultaneous existence in multiple states, or superposition, is precisely what gives quantum computers their immense potential. While a classical computer must process each possibility sequentially, a quantum computer can explore many possibilities in parallel, almost like trying all possible paths in a maze at the same time. The magic happens before observation. Only when a measurement is made does the qubit collapse into a definitive 0 or 1 state, much like the spinning coin finally landing. This intrinsic uncertainty is not a weakness but a powerful computational tool. If superposition is impressive, then quantum entanglement is truly mind-bending. Entanglement is a phenomenon where two or more qubits become inextricably linked, regardless of the distance separating them. When entangled, the state of one qubit instantly influences the state of the other, even if they are light-years apart. Measuring the state of one entangled qubit instantaneously reveals the state of its partner. Einstein famously called this spooky action at a distance, because it seems to defy classical understanding of locality and information transfer. The true power of entanglement for computing lies in how it allows qubits to cooperate and share information in a profound way. Imagine a network where knowing one part instantly informs you about every other connected part, no matter how complex. This interconnection means that adding more entangled qubits doesn't just add more computational power linearly, but exponentially. A system of many entangled qubits can represent an astronomically vast number of possibilities simultaneously, far beyond the reach of any classical machine, even the most powerful supercomputers we have today. Another fascinating quantum phenomenon, distinct from superposition and entanglement, is quantum tunneling. This is where a quantum particle can tunnel through an energy barrier, even if it doesn't classically possess enough energy to overcome it. Imagine rolling a ball up a hill. If it doesn't have enough momentum, it rolls back down. But at the quantum scale, there's a probability, however small, that the particle can simply appear on the other side of the hill without ever going over it. While not directly a computational principle like superposition, tunneling highlights the counterintuitive nature of the quantum world. Bringing these quantum phenomena into a usable computer requires extraordinary engineering. One leading approach involves superconducting circuits. These qubits are typically tiny electrical circuits cooled to incredibly low temperatures, just a fraction of a degree above absolute zero. At these extreme temperatures, certain materials lose all electrical resistance, allowing electrons to flow without scattering. This creates a stable environment where quantum states can be maintained for computation. Companies like IBM and Google use this approach to build their quantum processors. Another promising technology for building qubits uses trapped ions. In this method, individual atoms are ionized, meaning they are given an electrical charge. These charged atoms, or ions, can then be suspended and precisely manipulated in a vacuum using electromagnetic fields. Lasers are used to cool the ions to near absolute zero and to control their quantum states, allowing them to act as qubits. Companies like IonQ are at the forefront of this technology, showcasing the diversity of approaches in the race to build robust quantum computers. A more nascent, but highly anticipated approach, involves topological qubits. These qubits encode information in the exotic properties of topological materials, specifically in their surface and edge states. The information is not stored in individual particles but in the global properties of the material, making them inherently more resistant to local disturbances and errors. This approach holds the promise of greater stability and less susceptibility to decoherence, addressing some of the major challenges in quantum computing, though its experimental realization is still in early stages. Despite the extraordinary potential, quantum computing faces significant hurdles. One of the most critical is decoherence. Quantum states, especially superposition and entanglement, are incredibly fragile. They are highly sensitive to interference from the surrounding environment, such as stray electromagnetic fields, temperature fluctuations, or even minute vibrations. Any interaction can cause the qubit to lose its delicate quantum properties, collapsing its superposition and breaking its entanglement, effectively destroying the computation. Maintaining these states is a monumental engineering challenge. To combat decoherence, quantum computers require environments of extreme isolation and cold. For superconducting qubits, this means cooling them down to temperatures just a few thousandths of a degree above absolute zero, colder than deep space. These cryogenic conditions minimize thermal vibrations and electromagnetic noise, providing the serene environment necessary for qubits to maintain their delicate quantum states long enough to perform calculations. Building and maintaining such complex cooling systems is a major part of the quantum engineering challenge. Even with extreme isolation, errors are inherent in quantum systems. Qubits are prone to errors caused by residual noise or imperfections in control. Unlike classical computers, where error correction is relatively straightforward, a bit flip from 0 to 1 is easily detectable. Correcting errors in superposition and entanglement is far more complex. You cannot simply observe a qubit to check for an error without collapsing its quantum state. Advanced quantum error correction codes, which involve using many physical qubits to encode one logical qubit, are being developed, but they demand significant overhead and more qubits. The journey from theoretical concept to practical quantum computer is long and arduous, marked by ongoing innovation and breakthroughs. Research labs and tech giants worldwide are investing heavily, each tackling the challenges of hardware, software, and algorithms from different angles. This collaborative and competitive landscape is rapidly advancing the field, with new records in qubit count and coherence times being set regularly. While still in its early stages, the progress is undeniable, pointing towards a future where quantum computers could become invaluable tools for science and industry. So, with all these difficulties, why pursue quantum computing? The answer lies in the concept of quantum advantage, sometimes called quantum supremacy. This is the point at which a quantum computer can perform a specific calculation or solve a problem that is practically impossible for even the most powerful classical supercomputers. This isn't about simply being faster at everything, but about tackling a specific class of problems that classical machines could never hope to solve within a reasonable timeframe. It represents a fundamental shift in computational capability. Achieving quantum advantage isn't merely a matter of building a slightly faster processor. It's a leap to an entirely new computational paradigm. The exponential increase in problem-solving capability offered by superposition and entanglement means that certain computations that would take classical computers billions of years could potentially be solved by quantum machines in minutes or hours. This opens up entirely new avenues of research and development, allowing us to explore complex systems with unprecedented depth and accuracy, pushing the boundaries of scientific discovery and technological innovation. One of the most transformative real-world applications of quantum computing lies in drug discovery. Understanding how molecules interact at a quantum level is crucial for designing new pharmaceuticals, but classical computers struggle to simulate these complex quantum interactions. Quantum computers, by their very nature, are adept at modeling molecular structures and chemical reactions with high precision. This could dramatically accelerate the development of new drugs, leading to treatments for diseases that are currently incurable, reducing both costs and timelines in pharmaceutical research. Quantum computers also hold immense promise for material science. Imagine designing new materials with properties tailored precisely for specific applications, super-efficient catalysts, superconductors at room temperature, or lighter, stronger alloys for aerospace. By accurately simulating quantum interactions within materials, scientists could predict and engineer their properties at an atomic level. This could lead to breakthroughs in energy storage, battery technology, solar panels, and countless other fields, fundamentally changing the resources and tools available to humanity. The world of finance is another area set for quantum disruption. Financial markets are incredibly complex, with countless variables interacting in unpredictable ways. Quantum computers could optimize intricate financial models, improving risk analysis, portfolio management, and fraud detection. They might simulate market behavior with greater accuracy, identify hidden patterns, and provide more sophisticated strategies for trading and investment. This could lead to more stable and efficient financial systems, benefiting both institutions and individual investors by uncovering previously unseen correlations and opportunities. While quantum computing offers many benefits, it also presents a significant challenge to current cryptographic systems. Many of our modern encryption methods, like those protecting online banking and secure communications, rely on the difficulty of factoring large numbers. Quantum algorithms, such as Shor's algorithm, could break these encryption schemes with relative ease. This poses a serious threat to data security, requiring a new generation of post-quantum cryptography to be developed. The race is on to secure our digital future against potential quantum attacks. In anticipation of quantum computers becoming powerful enough to crack current encryption, researchers are actively developing post-quantum cryptography. These are new encryption algorithms designed to be secure against both classical and quantum attacks. The goal is to develop cryptographic methods that rely on different mathematical problems, which are believed to be hard even for quantum computers to solve. This proactive approach ensures that our sensitive data, from government secrets to personal financial information, remains protected in a quantum-enabled future. Let's compare the fundamental processing power. A classical computer's bit is like a light switch, either on or off, 0 or 1. It processes information sequentially, one calculation after another, even if very quickly. A quantum computer's qubit, thanks to superposition, is like a light dimmer that can be off, on, or anywhere in between simultaneously. This allows for parallel exploration of vast numbers of possibilities. The difference is not just speed, but a fundamentally different way of approaching and solving problems, especially those involving complex probabilities and interactions. Beyond the hardware, an entire ecosystem of software, algorithms, and specialized programming languages is emerging to harness quantum computers. Developers are learning to write quantum algorithms that can leverage superposition and entanglement to solve specific problems. Cloud-based quantum computing platforms are making these powerful machines accessible to a wider range of researchers and businesses, even those without their own multi-million-dollar quantum labs. This growing ecosystem is crucial for translating theoretical quantum advantage into practical, real-world solutions across various industries. It's important to clarify what quantum computers are not. They are not simply faster versions of classical computers for everyday tasks. Your email, social media, or word processing will not run better on a quantum machine. Classical computers are perfectly optimized for these tasks. Quantum computers excel at very specific, complex problems that exploit quantum mechanics. They are special-purpose tools, designed to tackle a limited but profoundly impactful class of problems that are intractable for classical machines, rather than replacing them entirely for general computation. One of the biggest remaining challenges is scalability. Current quantum computers typically have a limited number of stable, high-quality qubits. To solve truly complex problems and achieve widespread quantum advantage, hundreds or even thousands of logical qubits will be needed. Achieving this requires overcoming decoherence and error correction hurdles on a much larger scale, which means vastly improved hardware, more robust control systems, and innovative architectural designs. The journey to building fault-tolerant, large-scale quantum computers is still ongoing, a testament to its complexity. Despite the challenges, the pace of innovation in quantum computing is breathtaking. Every year brings new breakthroughs in qubit stability, coherence times, and control accuracy. While a universally powerful quantum computer might still be years away, the capabilities of current machines are already opening new avenues for research and specific problem solving. The horizon of possibility is expanding, promising a future where humanity can tackle some of its most pressing challenges with an entirely new class of computational power. Beyond finding direct solutions, quantum computers are inherently powerful simulation tools. Many complex systems in nature, from chemical reactions to subatomic particle interactions, operate according to quantum rules. Simulating these systems on classical computers is incredibly resource-intensive, often requiring approximations. Quantum computers, by mirroring the quantum world itself, can simulate these phenomena with far greater accuracy and efficiency. This capability alone could revolutionize fields like chemistry, physics, and biology, offering insights into the fundamental workings of the universe. It's not just about the hardware, the development of sophisticated quantum algorithms is equally vital. Algorithms like Shor's for factoring numbers, or Grover's for searching databases, demonstrate how quantum mechanics can be harnessed to achieve speedups for specific tasks. Researchers are constantly discovering and refining new quantum algorithms, each tailored to leverage superposition and entanglement for different computational problems. This interplay between hardware development and algorithmic innovation is what truly defines the progress and potential of quantum computing. Quantum computing is also poised to significantly impact artificial intelligence and machine learning. Quantum algorithms could potentially accelerate training for complex neural networks, enhance pattern recognition, and optimize machine learning models. The ability to process vast datasets in superposition might lead to breakthroughs in areas like image recognition, natural language processing, and personalized medicine, creating more powerful and efficient AI systems. This convergence of quantum mechanics and AI could unlock levels of intelligence and problem-solving capacity previously unimaginable. Beyond direct computation, the principles of quantum mechanics are also being applied to develop incredibly sensitive quantum sensors. These sensors can detect minuscule changes in magnetic fields, gravity, or temperature with unprecedented precision. Applications range from highly accurate medical imaging, improved navigation systems for autonomous vehicles, to dark matter detection and fundamental physics research. While not strictly quantum computers, these devices leverage the same quantum phenomena to achieve superior measurement capabilities, showcasing the broader impact of quantum technologies. Looking further into the future, researchers are even exploring the concept of a quantum internet. This would be a network that uses entangled qubits to transmit information, potentially offering unbreakable encryption and entirely new ways of distributed quantum computation. While still highly theoretical and in early experimental stages, a quantum internet could revolutionize communication security and distributed computing, linking quantum computers together to form an even more powerful global network. The implications for secure global communication are immense. Behind every quantum breakthrough are dedicated teams of scientists, engineers, and theorists pushing the boundaries of human knowledge. It's a field that demands interdisciplinary collaboration, drawing experts from physics, computer science, materials science, and engineering. Their tireless work in labs around the world, experimenting with new designs, refining control mechanisms, and developing algorithms, is what slowly but surely brings the promise of quantum computing closer to reality. It is a testament to human ingenuity and our relentless quest to understand and harness the universe. As with any transformative technology, quantum computing also brings ethical considerations. The ability to break current encryption, the potential for advanced surveillance, or the creation of powerful AI raises questions about responsible development and deployment. Discussions around access, control, and the societal impact of quantum technologies are crucial. Ensuring that quantum computing benefits humanity as a whole, rather than exacerbating inequalities or creating new threats, will require careful thought, international cooperation, and proactive policymaking as the technology matures. Quantum computing is not a distant science fiction dream, it is a rapidly evolving reality. While still in its infancy, its foundational principles, superposition, entanglement, and the unique properties of qubits, promise to unlock computational powers far beyond anything classical computers can achieve. The challenges are immense, from battling decoherence to perfecting error correction, but the potential rewards in drug discovery, materials science, finance, and cryptography are too significant to ignore. We stand on the cusp of a new age of computation, poised to redefine the limits of human capability and understanding. The journey into quantum computing is just beginning, a new chapter in humanity's quest to understand and master the universe. It's a field brimming with complexity, wonder, and the promise of unprecedented power. As researchers continue to unravel its mysteries and build ever more sophisticated machines, the line between what's possible and impossible continues to blur. The impact of this technology will ripple across every scientific discipline and industry, offering solutions to problems we haven't even fully articulated yet. The quantum realm awaits our exploration, ready to reveal its secrets and reshape our future.